Good morning, everyone. My name is Sophie Cross, and I will be presenting my project on measuring superfluid helium drop evaporation rates from surface mode oscillations on behalf of Harris Labs. In 1997, Andre Geim levitated a frog. And as Harrison highlighted before, levitation is not possible only through magic, but through magnets. As an object with paired electrons enters an external magnetic field, a weak repulsion between the magnetic field and the object occurs, and this can result in a frictionless suspension or levitation. But why is this important to Harris Labs? Harris Labs, we have three goals that can be categorized into three subsets of science or physics. We study high finesse optical cavities, fluid dynamics, and conduct a precision test of the standard model. And doing all this, we did all of this on a platform, which is a magnetically levitated drop of superfluid helium. This is the cryostat, which houses and cools our magnet. We have approximately a 15 Tesla magnetic solenoid right here, baths of liquid nitrogen and liquid helium in vacuum chambers that work as thermal shielding, and a sample space where our drop forms and resides. Here you can see our drop levitated, two mirrors here, and a window so we can send a laser light through it. Well, here's the magnetic field diagram. A video of our drop forming. Play this. Sorry. This is what we call the mist method. So when we puff helium gas into our sample space, and the cool inner walls from the liquid helium condense the gas, and droplets like mist or rain will form inside the magnetic trap, forming this drop. My project works on measuring the evaporation rate, lifetime, and temperature of the drop. So our drop can move in many ways. It can move with its center of mass in the XYZ axes, or its surface can oscillate while its bulk or the core of the liquid remains stationary. The ways that you can think about it like ocean waves moving on the surface of a sphere. Now, the ways that our drops distort are not random, but instead are determined by L nodal lines. Nodal lines being the two-dimension representation of nodes on a standing wave. Here we have our L equals 3 mode, where we have 1, 2, 3 nodal lines for our drop. Each nodal line can be oriented in a different way and rotated in a different way. So each set of nodal lines will have 2 L+1 configurations in which the drop is able to oscillate. This means there's a finite set of configurations in which our drop can move on its surface. So like any mechanic oscillator, our drop has a frequency at which it oscillates and a damping force. Here in our diagram, we have the red parts of these drops are where the drop is kind of curved inwards, and this is where the drop is protrude, forming outwards. I want you to picture the sound of a tuning fork, the high pure ringing. Now, this is an example of a high quality factor object where when it's hit as its resonant frequency, it'll ring and it takes a while for the object to damp out or the sound to stop happening. But a drum, when you hit it, it reverberates and it damps out very, very quickly. These graphs over the time domain are the ring downs or the time of decay of an oscillatory object to return to steady equilibrium. This is important because my project, I plotted, fitted, and analyzed ring down graphs of our surface mode oscillations. We take our laser and we drive at a certain frequency that is resonant to the drop's frequency or close to resonant frequency. And then we have a response from the droplet or a certain amount of movement in its surface. Then we will shut off this laser and drive at an irrelevant frequency and we focus on this ring down right here. And this is the decay of the drop's response. We do this many times to gather data and can take vital variables from it, such as the frequency of the drop and the damping rate of the drop. One part of my project was curve fitting for ring downs, where I would take the exact data, I would plot it, and as you can see here in this black, there's lots of noise. And then I would input unknown variables, amplitude A, omega naught, our frequency at which the drop wants to oscillate, and our damping rate gamma. And I would plug these unknown variables into a function in Python that I wrote to where the output would be a fit that, or the best fit parameters that would allow my model to fit the data as best as possible. So our equation here, we have our complex signal Z as a function of time, our amplitude A, e to the I, the natural frequency of the drop or its resonant frequency, which cannot be, which is an unknown variable, and then the demodulation frequency, or the frequency that we drive at, which is close to our resonant frequency. Then we have our unknown variable gamma, our damping rate, over t, and then time, the time of a ring down. Now, here are each data point in these graphs represent the best fit values returned from each fit. So each point represents one ring down, or the frequency for one ring down, and the damping rate for one ring down. Now, the frequency, it is important to keep in mind that the frequency at which the drop naturally oscillates, or its resonant frequency, is not exactly the frequency that we're driving at. Frequency that we're driving at remains the same throughout. It's our demodulation frequency. But however, the frequency of the drop, as you can see, it trends upwards. Why is this? Well, we can turn to a derivation of the Rayleigh formula for this, where we have an equation of a spring oscillator from Hooke, where the frequency of the drop is equal to a spring constant, or the frequency of an oscillator is equal to spring constant over mass m. The frequency of our drop is equal to what can be thought of as a spring constant almost, but the surface tension of our drop over the density, volume of our drop, as well as the L's, which are integers that represent the nodal line and connect the harmonics into our frequency. It's for harmonic oscillation. Now, just did 3 minutes. Oh, okay. Sorry. Now, constants, density, surface tension, are integers L's. So the only thing that is changing is the radius of our drop, meaning the frequency is inversely proportional to the radius of our drop. This is because our drop is evaporating over time. So evaporating, or one of the properties of superfluid helium means it has a self-cooling evaporation, like how humans sweat to cool ourselves. Our drop is evaporating. So here, at the time where it's a little hotter, our frequency is lower, and as our radius decreases, we get a cooler temperature and a higher frequency. This can also mean we can deduct that damping rate is correlated to temperature. Here we have a hotter temperature with a higher damping rate, and a cooler temperature with a lower damping rate. The damping rate we have is about proportional to temperature to the fourth. So one small change in temperature, as these are only matters of millikelvins over 15,000 seconds or 1,500 seconds, our damping rate will experience a big change. In conclusion, we can find the evaporation rate of our drop, which again is inversely proportional to the radius of our drop. Plotted here is a best fit line of our radius drop over time, and we can deduct the radius of this particular drop measured was about 40 picometers per second. The lowest we have seen in our drop measurements is about 0.1 picometers per second, which means that would take more than a century to decay or to fully evaporate away. well, this one take about roughly 2 months to fully evaporate. Yeah. I'd like to thank everyone in Harris Labs, especially Jack Harris, Igor and Theo for being my supervisors. And I am willing to take any questions about my project. Questions? Yes.
So when you were measuring the ring downs on the drops that were suspended by the laser, what kind of atmosphere are you doing this in? And I guess more importantly, like, does it matter?
Atmosphere, you mean where the drop is?
Right, like where the drop is it like surrounded by air, or is it in a like glove box atmosphere? Or
So our drop resides in the cryostat. Okay. Sorry. The cryostat's right here. Our drop is inside the sample space right here, and it is about at, I think the temperature of the drop is around 1 Kelvin, but the surrounding atmosphere is 4 Kelvin, cooled by liquid helium. And there's this magnetic solenoid around it. So the atmosphere of the drop is levitated in this area right here, surrounding by a temperature of 4 Kelvin.
okay, but it's just like room air that's in there, like around the drop.
I'm unsure about that. It's a
It's in
vacuum.
a vacuum drop. Okay. Okay, cool. Thank you.
Any other questions? Yes.
So in the earlier equation for z as a function of t,
Mhm.
like why is the gamma, like, should it be multiplied by the I, or you meant to put it outside as like an exponential decaying factor?
So our equation can be rewrote when we have e to the I omega t times e to the I gamma t. And basically these parts of the function are amplitude and then the oscillatory motion, which is right now it's, I guess, described as a complex number, but is real data. It is just sort of a derivation of Euler's formula. And then we have our decay rate, which is e to the gamma t. So that would be our decay rate. So it is not actually, your question was, why is
I think you hit the real part, then gamma is absorbed into the frequency, right? But you kind of mean it to be like a prefactor on some cosine of omega t. And maybe it's just a typo, I feel like, but maybe I'm also wrong.
I'm unsure of what you're asking, I think.
It is a typo. There should be no I in front of the gamma there.
Okay,
Oh,
never mind. It's all right, yeah.
Sorry, I did have one last question. Can you go back to slide 4?
oh, sorry.
Oh yeah, I meant this one. Okay, perfect. Yeah, sorry if you already mentioned this, but what determines the mode or yeah, the shape of the frequencies that you get for each sphere?
So we have two, I guess I would want to say, categories in which we can. L is the amount of nodal lines. So if you picture a standing wave with its nodes, that's basically what these are for the sphere. M is the orientation of these nodal lines. So if you look at m minus 1, you have one almost vertically oriented nodal line, and it's rotating in a certain direction opposite to m equals 1. So for every integer L, there will be 2L plus 1 configurations the drop is able to oscillate at. And typically we don't know what we're going to get if we are driving at a frequency that would respond with L nodal lines. We won't know if we really get m equals 3, m equals -2, or whatever until we really see it, I think. But I hope that answers your question.
Yeah, it does. Thanks.
Thank you.